I guess passing back papers just throws me out of my routine on doing these things. Okay, I think we're there. Let me close that tab. And as I was saying before, apologies to the student that pointed this out during the exam. That was a true typo. It shouldn't have been there. The best way to answer it would have been the center is approximately maybe 3.125. The spread is, depending on how you answer it, you might say the range from 0 to maybe 6.5, so a range of 6.5. But this question, I feel like, again, it was way too distracting to really make it a fair one. And because of that, no one lost actual points on this question at all. I put here on part A, but this was for the whole problem, number 4. So this one was kind of like a bonus. People did pretty well on it, except if you got hung up on the extraneous thing here. And I think people who read the instructions like this just described the shape, and they didn't see that part, describe the shape, because of the parallelism. People did better on that kind of thing. So it just looked like a totally unfair question because of that. But questions so far, folks? Let me pass back an exam at the moment while we're thinking about that. Didn't need to throw that. But that's how much pretty much how each exam is going to go in this class. It's going to be about 5 problems, give or take 1 or 2 problems, just depending on how long they are. But as far as the length goes, that's about how long I'm going to try to make each one of these exams. Once your exams are passed back, you get a fraction here, just the total number of points out of the 44. And I also update something called a course score on every exam. And that's just your grade in Moodle. It takes into account your MyStats lab, your quiz grade, as well as your exam 1 grade. So the way I calculated it was I went up here. I literally did this. I always double check. You have to get your Excel functions just right and not put in the wrong numbers. So your homework, that's the MyStats lab. And that one was worth 20% of the credit in the course. Quizzes were worth 15%. And I believe that was just out of the 3 quizzes that were due, if I recall correctly. And as far as exams, exam 1 is weighted as 65%, since it's just our only exam we have out right now. And that just gives you a rough idea of what your standing is in the class as of this moment. So it's a little confusing. Every exam has 2 grades. And the grade here gets converted to a percentage in Moodle, so that's even more confusing. And then you get a whole overall different grade here. This is the grade that updates in Moodle week after week. Well, any questions at all, folks, about the exam? Okay, well, congratulations. We got through our first one, first of 3 ordinary exams and then 1 final exam. Our next upcoming exam, again, it's pretty far out in the schedule. It's past midterm week, so it'll be on this week here, Monday, October 14th. We'll be midway through October. Even though it's a ways out, that means probably around this weekend or the weekend this week at the very, very latest. No, that would be way too late. Right around this weekend here, I'm going to have to start updating what's on exam 2, provide the review materials and those kinds of things. So it looks like we're getting pretty close to get that information filled out coming up. But right now, here's where we're at. We're working on normal models. And the next set of notes, working with normal percentiles, means we're doing the same thing. The only difference is we're using the calculator as opposed to the 68, 95, 99.7 rule. Also, our quiz 4 is due Thursday, and we'll post a new quiz, just getting back into that weekly quiz pattern. Any questions whatsoever, folks, before we get started? Okay, well, let's jump back in. Let's see, what were we doing? We looked at the normal distribution. Here it is up here. And we found that there's percentages given in these quantities for the distances you are away from the mean. For example, if you're between 1 standard deviation and 2 standard deviations to the left of the mean, left meaning negative, then that'd be about 13.5% of the information or data that you have in your sample. And between -1 standard deviation, +1 standard deviation away from the mean, that's taking into account to just about everybody. 68%, or roughly over 2/3 of your data set, is in this location. So using this information, As long as you have data that's unimodal, roughly symmetric, we can start modeling an entire population by this normal distribution. So that's what we were left off on our example 2 down below here. Might as well take a look at these. This was a picture where the normal distribution wouldn't be perfect, but it would work okay in this case. And this is a situation where you couldn't use a normal model whatsoever. The skew is just too severe for data like these. So we left right here on example 2. This was about the time it takes to respond to a brake signal in ordinary traffic light type conditions. And we're told that from admittedly a really old article in 1993, that the time it takes for an in-traffic response to a brake signal should be modeled with a normal distribution or a normal model, so that's kind of nice, with a mean of 1.31 seconds, standard deviation of 0.42 seconds. These are now parameters because we're trying to describe population with those values. We're not trying to describe them using any sample any longer. So this is our assumed best guess of the population mean and best guess of the population's standard deviation. Doing that, we use the percentages we looked at the top of the chart on these notes, and we drew the normal model. There it is drawn, kind of shaky hand. Looks like I had a lot of coffee that day. And we labeled it showing what the 68 to 95, 99.7 rule predicts. That just means we put down these tick marks. This is 1 deviation to the left, 2 deviations to the left, and so on. And we threw in the percentages. The way the computation went was we found the mean 1.31. To get 1 tick mark to the right, we added 0.42. So we have 1.73, and then we just kept on doing the same thing. To get to the next tick mark, add the standard deviation, 0.42. And now we're at 2.15 and so on. For these values going this way, we just subtracted the standard deviation each time to get to those last 3 values. Does that make sense to folks on how we built that chart there? Awesome. We'll do it again from scratch, but instead of just jumping right into the problem, I felt like we have to absorb this a little bit. It's always a long weekend coming back to this class. So now that we have a normal model, and we're modeling a population of times it takes to respond to a brake light, we can ask and answer certain questions. These are saying about what percent, but for just a preview, this whole question could be rephrased as the following. About what probability? So in a real sense, when we're using normal models, we're really dealing with probability. And whether you give a probability, that's just a number in decimal form, or percent, that's just a choice of unit. You're really doing probability when you're working with this model, which is kind of a fun thought. We haven't formally dived into a probability section just yet, but in a lot of senses, we've been kind of doing it here and there along the way. Well, about the question, it says, about what percent of the reaction times, so we're referring to the horizontal axis, those are the reaction times being mentioned, are predicted to be between 1.73 seconds and 2.57 seconds. So we want to be constrained between those 2 bounds. That means we take a look at our chart, and you'll notice every one of these questions, there's kind of a baked-in check. I can only ask a question that lines up directly with values here on this chart. So we have 1.73 starting here, going all the way up to 2.57, that's 3 standard deviations away. When it asks for about what percent, we just want the area. 13.5% of the area is here. It goes up to this, stops at the boundary at 2.57, and we pick up 2 numbers, 13.5. Exactly. Add the next region, 2.35. We have to throw it to the calculator, but that's pretty much it. So really, the major fighting is actually writing down the diagram. Once you have this, it's just a matter of using the information above to extract the right numbers. So we'll take 13.5, add 2.35. So altogether, we're at 15.85%, close to 16%. So it's kind of a weird numbers they asked, but imagine that you're driving a car, you hit your brake light. If this model is accurate for the population of drivers in Idaho Falls, then about 16% of the time, they will take between 1.73 and 2.57 seconds to notice you and respond. Kind of shocking, but it is a slightly small percentage. Any questions at all, folks, with how we're calculating these so far? Okay, so that's pretty much the name of the game. When they ask about what percent, oh, he control Z that. When they ask about what percentage, that's kind of hard to take off. If we zoom in on this, we can do it. Sorry, Microsoft is sometimes a little bit picky with digital ink like that. There we go. So all the information is going to be pulled from this chart some way, somehow. But the reason we need a calculator in the next section is what the question was 1.70 seconds. That's even a worse approximation. And we're already approximating by using the 68, 95, 99.7 rule. So that's where the calculator is going to start to help us out when the questions don't line up with these tick marks on the axis so well. But let's try this again. Next question asks about what percent, so we're describing percentages of before, of the reaction times are predicted to be below 0.89 seconds. So we have a direction here, might as well highlight that. But part C and part D, the way we grab the percentages are actually a little bit different. This is below 0.89, but then there's no stopping. Starts here, we move off to the left, going this way, and to the left forever, even though values don't make sense at zero, they don't make sense when they're negative. The normal model has this weird feature where it does approach the x-axis rapidly, but it does go to the left forever. There's always area further and further to the left, even though those would be negative values that don't make sense. This is the sense where we're really modeling a population by something imperfect. This is not reality, it's just our best guess about how these brake lights are going to operate using that model. We'd always want a better model, but the normal model is just really fast to apply. Then once we find the region we're dealing with, below 0.89 seconds, we grab these percentages. Oh, that's the wrong color I want to use. It asks for about what percent, and so we'll grab these. Just kind of highlighting the way it's easy to delete this time. So we're just about there. We take the far left tail, we calculate this one to be 0.15%. Add the next region, 2.35%. So up to here. Then we stop at this one, 13.5%. Only because it said below 8.89 seconds. So we can't go any further to the right. Does that make sense to folks on how to grab those percentages? Awesome. The nice thing about this process is now it's just a matter of adding up the numbers. Usually for this kind of problem, we don't round at all since these are considered to be fully accurate in their approximations. So we just use the numbers we get. So let's go 0.15 plus 2.35 plus 13.5. And well, I guess I should have guessed that, right? We were just 0.15 off on this computation. So they're very similar, but dead on 16%. Could have saved some time in the calculator, but no harm doing extra practice, I guess. So that's two questions down, 16% chance that the person breaks at 0.89 seconds or sooner is what this is predicting. Again, it's just an approximation of reality. It's our best tool to model a population. Any questions, folks, with that one? Okay, next question is a little bit different from the others. Let me just try to reset the highlighting. Move this up so we don't have to scroll too much. And here's our next question. Describe the reaction times for the slowest reacting 16% of the population. Well, that's kind of an interesting question. When it says slowest reacting 16% of the population, well, first we know we're talking about percentages, but what end of the actual diagram are we on? This is reaction time. Are we on this end or are we on this end? Some say left or right. It's kind of tricky. Good call. It's that context right there. These problems are kind of tricky in the sense that even if you have the total diagram here, you still have to think about the context every single time you do a problem, because sometimes the questions are worded in a way that if you don't know the context, you're not sure which end of the diagram you're really working on. Kind of annoying in a way, but context is always one of the trickiest things about statistics, keeps coming back. So because these are reaction times, we'll consider slow reaction times to be on the upper end, more time. So we're on that end of the diagram, the far right. When it says slow is 16%, well, we would take this percentage, and that percentage. We know those add up to 16% exactly. We did it here on the left tail. But then that means we're using that number, 1.73. This goes off to the right forever, and we would say 1.73 seconds or longer. So that's going to describe the slowest reacting 16% of the population by that model. And always saying by that model is just a way to give a disclaimer. We don't expect that to be 100% accurate, but we think that this is close in how drivers would really react. So slow as 16%, not horrible, but that's close to 2 seconds or longer. Any questions, folks, on how we got that 1.73? Okay, so if it said, say, slowest, let's add plus 0.34. If they said, oh, let's subtract 0.34. I want to take 16 plus 34, rather. If it asked for the slowest 50%, then the question would have gone this way. We're then dealing with this number, this number, this number, and that number. That's the extra 34% I added. The reaction time that describes that would start at 1.31 seconds, right at the sample mean. That's kind of curious on its own. The sample mean cuts the upper half and the lower half directly in two, just like the median would. But this curve has perfect symmetry, so it behaves exactly like the median in that regard. Let's put this back to where it was. So we did it, folks. That's pretty much all we're doing in these kinds of problems right here. Just finding these probabilities or finding values on the x-axis that match up with the probabilities or percentages, 16%. Any questions at all with getting through this one? Okay, let's try it all over again. And then after the next problem, we'll do the exciting thing of showing how does it go in the calculator. So next problem down below. It's a bit of a longer problem. Looks like it has a good amount of context going on here. Starts off by saying, a company's manufacturing process uses 500 gallons of water at a time. A scrubbing machine then removes most of a chemical pollutant before pumping the water into a nearby lake. So it sounds like something familiar. Industry is costly and they use corrosive chemicals or just straight up neurotoxins like lead. And you have to know what to do with that water. In Idaho, the laws on that are kind of shaky. So bad things like this could happen all the time. Here it says, legally, the treated water should contain no more than 80 parts per million of the chemical, whatever it is. Think lead if you want just a good picture in your mind. Very bad neurotoxin. But the machine isn't perfect and it's costly to operate, and so there's the drama. They know they're legally supposed to remove the pollutant, but they're also trying to make money at the same time, and so a corporation's going to try to find a middle ground where they're barely in compliance, but making the most amount of profit potentially. So government agencies know this and they're going to impose fines. And so here's the corporation trying to find a middle ground. It goes on to say, since there's a fine if the discharged water exceeds the legal maximum, the company sets the machine to attain an average of 75 parts per million for the batches of water treated. So they believe the average is now 75 parts per million. Let's highlight that there. And by the way, if you see average, just think mean. Always a synonymous in this class. Oh dear. Let me fix that real quick. We always use blue for mean, I believe. I'm going to try to keep that color coding consistent. Goes on to say, they believe the machine's output could be described by a normal model. So normal distributions back on the table with a standard deviation of 4.2 parts per million. Oh, I have this weird highlighter tool going on. I'm not sure how to go back. Okay, there we go. Standard deviation of 4.2 parts per million. So we've got it, folks. That's the read of the whole, or the description of the whole problem. So they're averaging at 75 parts per million. It should contain no more than 80 parts per million. And so they feel like, that seems right. Except the average is never, ever the full story when it comes to these kinds of things. Standard deviation is kind of large. And so we wonder, is that large enough to get the company in trouble potentially? Well, there's a couple follow-up questions we'll ask and answer along the way to see if what the company is doing is ethical. So first thing it says, state the values of the parameters, use appropriate symbols for each parameter. Anyone recall what the symbol is for this one as an average? It'd be mu, a good call. Y bar wouldn't necessarily lose you a whole lot of credit on this problem because you're thinking along the right tracks. Y bar is an average or a mean. But if you're modeling a population, we use the parameter to display that. So we'll say mu is 75 parts per million. Excuse me. Likewise, this one is sigma. Looks like a weird little O with the tail on the right end. Sigma is the population standard deviation of 4.2 parts per million. So again, on paper, the company looks like it's doing a good job with the average set to 75, well below the requirement of 80. But now we're going to see what the situation really looks like when we bring in the population standard deviation. So think of this being like S, except S only describes the sample. This is describing the entire population of every single batch the company is going to release back into the lake. So that's our population. You know what? That's a tricky population. Let's say it right here, just for a little bit of practice on that. The population, these are follow-up questions we will look in later on. The population is all batches the company, they say, pumps into the lake, assuming that these are batches where they use the scrubbing machine to try to remove the chemical pollutant up to an average of 75 parts per million. What's tricky about populations is that sometimes it has a time component as well. For example, we were talking about the Fukushima meltdown and the population of salmon before the meltdown versus the population of the salmon after the meltdown were different. For a situation like this one, the population, when we say all batches, we might mean all future batches as long as this program is being run and the machine is tuned to those parameters. So some of these batches may not even exist yet. We're thinking about a population in the future if this machine runs for month after month. Kind of a strange population in a certain sense. But at the end of the day, we're just going to answer these questions with a normal model. So here's the fun part. Draw the normal model for this population and clearly label it. Usually we just start with a horizontal axis going this way. Let's add a little bit of space though. So here's our elongated horizontal axis. Good idea to put some description here. This was parts per million of a chemical pollutant. So let's say parts per million of the chemical pollutant. Okay, so now we know what our axis represents. You don't have to do that each and every time, but while you're practicing these kind of problems, not a bad idea. Now, for the normal model, one thing we mentioned is you don't have to be super artistic. It doesn't have to have perfect symmetry, but keep in mind, it can't ever go like this because your curve has to always be above the x-axis. Other things to avoid is your curve can't do this either. The right tail looks right, but on the left tail, something funky is going on. The curve, when it starts to move to the left, only gets closer and closer to the x-axis. It never turns up, in other words. So I wouldn't be super picky on grading these kinds of things, but those are just things to avoid. So if I try to do a decent one, sometimes going a little bit faster and not overthinking it does an okay job. I think this is the best one all semester so far. After we put that down, there's 5 numbers we need. one for the direct center, then 1, 2, 3 tick marks going to the left. 1, 2, 3 tick marks. I said that wrong. Going to the left that way, going to the right that way. And in the center, we put in the mean, 75. After that, it's just a matter of throwing things into the calculator. So let's work this through. Start with putting in 75, then add standard deviation 4.2. Sometimes it's not a bad idea to just do this all at once. Go plus 4.2, plus 4.2, and these last three outputs in the calculator are the last three tick marks going to the right. So it comes out as 79.2 parts per million, then 83.4, finally 87.6 parts per million. And if you run out of space like I almost did, just write your number sideways, and that's totally fine. That's why I usually like to make my horizontal axis a little bit bigger to fit everything in. After doing that, turn around and go 75 minus 4.2. So that's one tick mark to the left. And I'll keep the strategy. Let's go minus 4.2 again, minus 4.2 again. So these three numbers are on our left tick marks, starting at 70.8. Then 66.6, slightly evil number, and then 62.4. So there's our normal model. Next thing we need are the percentages. So let's put in this and this. I like to break this in the middle just in case a question corresponds to a 70.8 and a 75. Anyone recall what the probabilities or percentages are in these regions, here and here? 34, good call. That comes from the namesake 689599.7 rule. So we put 34 here, 34 here. And this is where it gets a little bit foggy for me. I think the next one's 13.5%. Strategy is just memorize one direction and you're good shape, or good thing to put on the notes. 13.5%. Thanks on that one. I think that's the one I'm most likely to forget. 2.35%. And then finally, 0.15%. That's the one that we calculated on these notes. So we have it all going to the left. We just duplicate going to the right with the symmetry of the curve. So 13.5, 2.35, and 0.15%. Liberal use of arrows might be a good idea unless you can write really small. Now that we have all that out, we can start answering these questions pretty rapidly. Any questions at all, folks, on coming up with the model? Okay, so it goes this way each and every time. The only thing that's going to change are your numbers, essentially. Let's come down here. They ask, what amount of the chemical pollutant? So if they're talking about that, we're trying to get something off the x-axis. Describes the 2.5% of cases for which the water is the cleanest. We have to decide, cleanest water, is that going to be the left tail or is that going to be the right tail? Some say to the right. How about to the left? Anyone for to the left? Yeah, go ahead. Yeah, I agree. To the left for this one. Again, it's a really tricky question, in all honesty. Every time I see these kinds of things, I have to do like a mental double take and remind myself, wait, what is the thing we're describing? The x-axis is the concentration of the pollutant. So cleanest means less polluted. We're on this end. Very tricky though. Does that make sense on why the left tail? Okay, so for satisfied with left tail, we want a certain amount, so we need a value on the x-axis so that we have the 2.5% of worst cases. Starting on the very far left, we're at 15%. Move over a little bit more. 2.35 plus 0.15 is exactly 2.5%. So that tells us we are in these two regions. And the number we're using is going to be that one. Does that make sense, folks? Why the 66.6? Okay, so that's the boundary where less and less pollution occurs, and the percentages total to exactly 2.5%. So we will say 66.6 parts per million or less. That describes the 2.5% cleanest cases. Remember, this is all about some kind of chemical or some kind of corporate entity producing some sort of water that they're trying to remove a chemical pollutant at. And now we're saying, well, 2.5% of the time, it's at this amount or less, 66.6 parts per million, which is fantastic because you have to get under 80 parts per million legally for this situation, whatever the generic pollutant is. So on that end, it looks like this is fantastic, except that's a small probability. Most of the time, you're somewhere out here. Remember, the cutoff was 80. There's a significant amount of area here that's going beyond 80. Let's maybe add that to the diagram since it's part of the context. Right here at 80, oh, sorry, I missed a chat up here. Sorry, Courtney, but you're absolutely right. It's supposed to be the left. Sorry, I missed that chat from earlier. But 80 parts per million was, or let's say is, the legal limit. So that's concerning once we build out this diagram and we see, hey, there's a chance, pretty good chance we're beyond that legal limit. But let's look at the next follow-up questions. Let me reset the highlighting first. Now we're asking about what percent of batches have more than 79.2 parts per million of the chemical pollutant. Notice how parts C and D are kind of backwards. Part C gave the percentage. We want to find the value on the horizontal axis, the 66.6. But now, part D, they gave us a value on the horizontal axis, 79.2. There it is. I think I deleted a tick mark. There it comes back. So having more than 79.2, we need to just find these three regions. There they are. Guess they were easy to find. And just add up those probabilities. Feels like deja vu almost. I think that's 16%. Does that sound right? Awesome. Let me put it down on paper just so we see where they came from. So 13.5 plus 2.35 plus 0.15, coming out at 16%. So deja vu for sure on this, but one thing you might notice is I only have 7 different tick marks here. There's actually not a ton of different questions you could really ask. So sometimes the questions feel like they're kind of redundant in a way. The question you really want to ask is, what's the percent chance you're above 80 parts per million? Because that's a percent chance that they're going to get a fine. But notice we can't actually answer that based off the 68, 95, 99.7 rule. Our questions have to line up directly with these tick marks, 79.2, 83.4, and so on. So there's definitely some drawbacks from computing this way. But at least it gets us started. So next it says, part E, what percentage of batches, so we're back defining a percent, have between 70.8 parts per million and 87.6 parts per million. So this time we're constrained between those two values. These are values on the horizontal axis. So we start here, 70.8. We're going up to 87.6, so that's way out there. So this is the range on the horizontal axis that we're taking. That's our first step. Look at where we're going, left to right on the horizontal axis. Because it's asking about what percent, we will grab above these regions, these percentages. Let's see. And we don't pull the 0.15% because we stopped right at 87.6, which is relative to the 2.35. So in this problem, we would take 34 plus 34 plus 13.5 plus 2.35, and just tally those. That shouldn't be too bad. First two is 68%, plus 13.5, plus 2.35. So we've got it. It is about 83.85%. And we did it. That's finding percentages based off the normal model. So we're saying there's an 83.85% chance that when this machine runs, the next batch is between 70.8, 87.6 parts per million of the pollutants, let's just say lead. Any questions at all, folks, on finding that last probability percentage? Awesome. Again, this is kind of unsatisfying in a real way. We ran out of questions. We didn't ask the big one. The big question everyone would want to ask, especially if you own the company that's dumping these batches into the nearby lake, is what is the percent chance that we're going to get a fine for the governing body that's watching these kinds of things? We can't answer that at all with this method, but let's do a really quick preview because I think we're all just dying to know. Let me just get these highlights off real quick. Let's call this just a follow-up question. Or maybe better, let's call this a preview question. What is the percent chance the company will have to pay a fine? We can answer it, but we have to use technology to make this happen. Back in the old days, what people would have used is z-scores and something called a z-table. Let's actually show that just to get a feel for what in the world that is. When I say back in the old days, that's not too long ago, actually. Where is our z-table? There it is. People used to calculate probabilities by doing a z-score, count the number of standard deviations you are, and then just find the right value on your z-table that corresponds to the probability. It's extremely tedious, it has limited precision, and I have ads popping up everywhere. Let's get that out of there, jeez. So we're not doing it that way. And the reason I'm mentioning that is in the next section, our author does a z-score step, but we're going to skip that step. We're going to calculate these probabilities directly. So again, this is just a preview, but if you have your calculator with you, this is what we're going to be going over in great detail in section 5.4. To answer this question, we have to say what's the value for paying a fine. It's at 80 parts per million or higher. So let's start by saying a fine is incurred at 80 parts per million or higher for the pollutant of those batches. So we'll do this in the calculator. Again, this is kind of a preview, so don't worry if the steps look a little bit crazy. We're going to be going over this a lot in section 5.4. But the first thing we'll do is hit the second key, in blue on this calculator. We go over to where it says vars. We're trying to hit the distribution button printed in blue. So second vars pulls up this window here. We have a lot of different probability distributions. In this course, we'll be using the normal distribution as well as the t-distribution quite a lot. And what we want is something called normal CDF, kind of a vague word, to enter on that. And it's asking for lower, upper, well, mu and sigma, that definitely looks familiar. What's lower? It's like a cutoff. It's that value right there. That's the lowest value we want to take because we're trying to find this area. That was supposed to be a marker. There we go. We're trying to find that area going to the right. So our lower value is just the lower bound. 80 parts per million we wrote down here as well. So we just throw in an 80, hit enter. And now we're in a really awkward position. We're going to discuss this a whole lot more, but recall when we said the curve doesn't actually stop here. It goes to the right forever. If I put in, say, 90, I'm not going to get a fully accurate answer. I want to put in something that represents essentially an infinity, a number where we're not ever stopping. You can't actually put infinity in a calculator like this. It's a finite machine, but you could put the best closest number. Go 10, hit the power button, that's this up arrow above your division, and put in 99. This is the largest supported number on the entire calculator, and it's our best way of saying infinity. So we're going to the right non-stopping, essentially, for all numbers that make sense, and a whole bunch of them that don't. So hit enter on all of that. Well, don't hit enter too many times. If we enter through this field, we're still going to have a problem because the mean is 75. So we have to put that in. This is why we don't need z-scores. Our calculators these days allows just to put in the mean and the standard deviation sigma without subtracting the mean and then dividing by sigma like we did with z-scores. We still use z-scores. It'll be used later on, like we mentioned. Next, put in 4.2 for sigma. Then at paste button, all I'm doing is just hitting enter a bunch of times, and we get that percentage. It's going to be approximately a 11.69% chance of this occurring. So pretty significant. There is above an 11% chance this company really will be fined if they set the mean at 75 parts per million. That's because their machine is not perfect. There's variation in how well it does, batch to batch to batch, and that is a significant standard deviation. They should probably drop that down to 70 or 65. But then you can imagine there's going to be a big fight in the boardroom because if they do that, it's just going to be more costly. Their profit margins attack. So this is what goes on in statistics. You know what you're supposed to do, and the company's trying to find probabilities of doing the least amount that they have to do to be in compliance. But this looks like they would actually really retune their machine and set it to maybe 70 parts per million or something different. Well, any questions, folks, with the preview question there? Okay, let's look if it even seems accurate. This is about 13.5% in this region, so we're taking some of that, 2.35% here, and 0.15%. You know, it looks kind of concerning, but when I look at my value 80, it should have really been about there. The shading would have been a little bit more accurate. So my diagram didn't look accurate until 80 is about right there, really. So we are taking that area, and now suddenly it really does seem like it'd be 11%. Let me just move this arrow to the more accurate location. So just to pause here for one more moment, we might ask, what would happen if they moved the mean to 70 instead? That's a really fast scenario to run because you could just hit second, bars button again, go back down to normal CDF, and just move this to 75. Oh, no, keep it at 80, not 780. Delete there. What we're imagining is, what if they change the mean to 70? So let's drop this to a 70. We'll see what happens to the percent chance. If they make this slightly more ethical, set the mean to 70 parts per million per batch, then the probability of paying a fine is suddenly less than 1%. So it's kind of curious that they would have set it to 75 at all when just that slight retuning drops their risk of paying a fine. But maybe the fine just isn't very much. They're just willing to pay it. Who knows? Well, any questions at all, folks, running through that full problem or the preview question? Okay, this is what we're going to be doing in the next section. And what makes it all tricky is you'll observe that the calculator, the TI-84 Plus, really feels like a black box. Normal CDF, we didn't even say what CDF means. Let's say it here. CDF stands for cumulative distribution function, which is a weird statistics way of saying accumulate all of that area and tally it together. That's what normal CDF does. It gives us areas. We'll be looking into that quite a lot in the next section. But before we get too far, there's just a small discussion on parameter versus statistic. So we love to have a parameter in every single situation in statistics, but it's just never really feasible. Even if we're modeling with the normal population, when we say something is a value of mu, well, that's just a guess. They guess their machine is operating at that amount, but maybe the machine is becoming degraded. That value could change. Same with this value, 4.2 parts per million. That's also just a guess. The way you have to actually calculate a parameter is you have to sample the entire population. That's because the parameter describes that entire population. You need everybody in your sample now. So that's where statistics runs into another problem. It's really all about money. Even if they could take a census, they often won't because that's a humongous sample size in many cases. They would rather take a small sample and save lots and lots of cash. If they do that, they're calculating a statistic, but there is a benefit to this. So let's write out here just a short write-up. In almost all cases that we consider, the parameters are unknown. So what we do instead is we take a sample and calculate the statistics. So the statistics are known values. That deserves an exclamation mark because now we can say, for example, mu is something we're going to estimate quite a lot. It will be approximately equal to the statistic y bar. Likewise, sigma, we won't do a lot of hypothesis tests or confidence intervals on sigma, but it is still true. We'll make this estimate. Sigma is approximately equal to the statistic S, the sample standard deviation. So like before, we can make these estimates, but we still run into a major problem. These estimates are only useful when we describe the error in estimating. That sounds redundant. When we describe the error. In other words, we have to say just how accurate every one of those approximations are. That's why we're doing probability, and the normal model is a big step in that direction. Really, we're just calculating probabilities when we use these functions here. So that's just a quick refresher on parameters and statistics because they're a major part of inferential statistics. But any questions at all, folks, with the conclusion of the notes? Okay, well, let's save this up. Think of section 5.3 as it's useful, it's important. There's a picture in your mind's eye every time you use a calculator now, but it's not going to be the major emphasized section. It's like a warm-up to section 5.4. So let's go to 5.4 next and see how it goes. This is called Working with Normal Percentiles, kind of an interesting title. And starting this off, we have the reminder that this is always the picture that we're going to plot. But for the folks who are really curious about this, that curve, the mound-shaped symmetrical curve that we've been working on, is a true mathematical function that we could plot if we really wanted to. That's the function. It's horrible. It's really nasty to work with. It contains symbols that are potentially unfamiliar. For example, that symbol E, that's a number. E is approximately 2.71. It's irrational. Of course, there's pi, another irrational, approximately 3.141. I know pi to 3 digits, that's all. But there's a whole bunch of other things going on here. Notice it contains a sigma. And it also contains a mu. So the parameters are what specifies the shape of this curve in every single way. Change sigma, change mu, everything else remains the same, but the curve will change. So I thought it'd be nice to actually sketch out these curves for different values of mu and sigma, actually using technology this time, not freehand sketches. When we do a freehand sketch, the picture always essentially looks like this. If you make technology do it, here's the pictures we're going to start to get. So my favorite graphing calculator is Desmos, just because it's easy to use in class. That's the only reason. And this is not a problem that you will have to do in a class. This is more just a demonstration to show you what these curves are going to look like. So first we have to put that in. That's the worst part. F of x equals. It's 1 over, and I think if you hit Alt 239, nope, I have a cheat sheet here. There's a way to get a sigma. It's Alt 229. So go Alt 229 to get your sigma value. There it is. Add a slider just means that's a value we're going to change around. At the moment, it's not doing anything too special, just a horizontal line, 1 over sigma. Then it's going to be still in there, square root 2 pi. Now we're at this part. Put in E, it's just another number, about 2.71. Here's the power position, minus x minus, and for mu, it's Alt 230. There it goes. It doesn't know what that is. Let's just put in mu for mu. Let's go just m for mu and call that mu. So now we have a slider for the mean. Notice as we move the mean, it's changing where it's centered at, looks like. But there's more to this. That's raised to power 2. Now we've kind of collapsed it down here. And we divide by 2 sigma squared. 23229 for sigma squared. So finally, that's our curve. Doesn't look too pretty, but let's do it when mu is 0. So m is our mu on this one. There it is at 0. And sigma is exactly 1. So value of 1 would start right here. Let's see if we can fix this. The thing about sigma is that it's never negative. So let's say we go from 0 to 10, step size 0.5 just to make it easier to put in. So now here's sigma at 1, here's mu at 0, and that's our graph. Notice it doesn't seem anything at all like that one. There's commonalities, right? There's similar shapes there. But the reason we always plot it this way, like we see here, is that the shape that you see here just depends on how you scale your axes. For example, the scale I have on the vertical axis is not too convenient. There's nothing down this direction, and we're not going much higher than 1. We're not going higher than 0.5, really. So we can change the y-axis by going, say, let's make this a -1. And let's go to or just a +1. Slightly better picture. And now that shape really is kind of emerging. Let's see if we can make it even better. Let's go up to 0.5, -0.25. And now I think you'd agree it's starting to really kind of overlap with that picture. So when the mean is 0, standard deviation is 1, we get that shape. Notice right around -3 standard deviations, the curve is really close to the x-axis. In fact, if I go way out here, looks like it intersected with the x-axis. But that's not actually true. Zoom in anywhere on this, and here's the shape that you start to see. Just might have to be a while. That's 5 standard deviations, so patience is part of this process. Here we go. 5 standard deviations is a lot, but when we find percentages, it's percent of a total. The total area under that curve is exactly 1. That's pretty impressive. As you go to the left forever, there's always this kind of separation. You're always getting area to the left, always getting area to the right. And now it starts to seem kind of weird. But let's add these facts to this display right here. The curve has an extent of -infinity to infinity for its domain. So that's a way of saying it goes to the left forever. going that way. It goes to the right forever, going that way. The next thing we can say is, let's call this just fact one. Here's the next surprising fact two. The curve never hits the horizontal axis. So that's surprising. Now, if you ask just about anybody, me including, and you say, hey, there's always area because the curve never hits the x-axis and the curve also goes to the left forever, I would have assumed that the total area is infinite. There's no way it's finite area. But there really is. That's a weird thing about the normal model. It turns out the curve approaches the x-axis so rapidly that bullet three, the most unbelievable one, is actually true. The total area under the curve, by that we mean under the curve and above the horizontal axis, is exactly 1. Deserves 2 exclamation marks, because that is really pretty bizarre, but that's the model we were working with in the last section of notes. A very, very weird model, because if it goes to the left forever, it's going to contain values that don't even make sense in your diagram. For example, when we were talking about brake lights, when we drew out that model, we stopped at 0.05 seconds reaction time. It actually goes to the left even further into the negative values. Negative values don't make sense for a reaction time, but we still use the model because it went to the horizontal axis so fast around the nonsensical values, we decided the model is still doing a decent enough job. So there's almost no probability on the far left, the far right. And that's why this becomes less weird the more you work with it. But any questions so far, folks, with those weird facts about the normal model so far? Okay, if you don't believe all facts taken together, I understand. It is almost seems like a kind of paradox in a way. But more math classes you take, the more these kinds of things do get resolved. So let's go back to the calculator. Let me see if I can fix the zoom on this. Let me just put in values so we're not scrolling all day. Let's go from -3 to +3. Actually, let's go a little bit further left and right. -5, +5, and our zoom of -0.25 and 0.5 did a pretty good job. So there's our picture. Let's put it down in the display. I'll take a total screenshot just in case you want to come in here and play around with this kind of stuff. This is how we implemented it. This is extraneous though. What we want in this class is more of the pictures. And this is for people who would like to play around with that kind of stuff. So here's our screenshot on the very first one. I believe it will, but it's just a little bit trickier to get it in. You'd have to use on the calculator to hit second bars, and I believe it's under draw. No, hang on, it's not draw. That's shading in a certain way. Let's see. I'm actually not too sure how to do it in the calculator. That's something I'd have to come back to. I believe they would use normal PDF because that gives you points on the graph, but then we would have to tell the calculator to actually plot all this stuff out. That could be kind of tricky to make happen. But let's just play with that now that you mentioned it. If you use normal PDF, it wants an X value. Let's give it 0 just to see how it works. It wants a mean. We have it set to 0 and 1 already. And it gives us the 1 point, 0.39, which we saw here. We might have assumed it was 0.4, and that looks about accurate now. By the way, this is one of the reasons why we never actually plot a vertical axis. We're not too worried about the numbers in the vertical direction. It's about the horizontal direction we care about the most. In these plots, it does provide it, but it's a limited value. Other questions so far? Okay, well, let's start changing this up. This is where it gets a little bit more interesting, I'd say. Part B, we're changing something. Mu is becoming -2, sigma stays at 1, but what would you all predict happens if we set mu at -2 to this picture here? It won't go below the x-axis, but it does move. It does shift left, exactly. The top here, whatever it happens to be, corresponds to the mean value of 0. So if we move the mean to -2, we should see that change as well. Let's give it a try. So here's at 0, at -2, that's where it ends up. So in that case, we call this really a location parameter. Measure of location is what we called it earlier in the section when it was a y bar, because it's just saying the location of the peak in your display. For these ones, I'm just going to take a limited screenshot, stuff that looks more like this. So that's what happens if we set mu to -2. We're just affecting where the peak ends up. So we often say that this is a location parameter. But this one, sigma, we're going to change in the next problem. It's called something different. Sigma is a measure of spread for sure, but in this context, this is a shape parameter. So let's look at what we're doing. We're putting the mean back to 0, so that's no big deal, right? Just imagine this center is at 0 here, but we're changing from a standard deviation of 1 for the population to a standard deviation of 10. What will that do to the curve? Well, this is also a measure of spread. If it's higher, we imagine the data is spread out even further. So that curve we see in red should start to become more spread out. Let's see if we can make it happen. Any questions first? Okay, so back to the graphing calculator. Let me just make this bigger so we can hide the last problem. We're putting mu back to 0. There it goes. And now we're changing the spread of the data. It went from 1 to a factor of 10 times more spread out. So here's our picture. Spread out times 10 looks like that. We're back to a really weird curve. Again, we're at 1. We're saying that's the spread of the data. We make it smaller, that the data is less spread out. Starts to do that. It's peaking around one certain little spot. We need a different zoom for that. But if we increase the spread, all that area gets spread out as well. So here's it back to 10. We would never draw something like that if we were in the last section when we were drawing the normal model. And yet we would still try to draw that, even though our picture is super different this time. What's wrong is look at our scale. If we have a standard deviation of 10, the left should be going to about -30, and the right should be going to about +30. The trouble here is we're way too zoomed in. Let's see if we can get a better zoom on this. So let's use this tool just because it's less scrolling. We should be going to say -30 this direction, +30 in that direction. Still doesn't look like a curve we would plot, but we can also fix the y-axis again. Let's go from -0.1 maybe, yeah, it should work, to 0.05. And we're back to the same exact display. So the shape the normal curve takes is completely a function of how you zoom in on it with your display. It's for that reason we always just draw it that way. We don't put in the vertical axis, we just assume that the scale is right to give that shape each and every single time. So let's put down that next one. Again, kind of a nice little shape. So looks like it's more spread out. You can't really tell until, again, you look at what happened out here. Lost the number, that was 30. So that's how we can tell the data really did get more spread out by the shape parameter. And yeah, it truly does affect the shape. We can see it happen in real time that way. By the way, if you do something crazy like putting in a 0, the whole thing's gone. You really have to have something positive. Imagine 0 being really like the worst reality ever. It would say that there is no difference between anything. If this was a problem about people, it would mean everybody's the exact same height, no variation. Everyone has the same eye color and so on, so on. Real data has variation, so you'll see a picture like that at the worst. But if you just change the shape, the way you zoom in, it still goes back to that kind of picture. So those are the major things we were looking at. Let's do one more just because we can. Here at point 1, it would go to about this. I don't know if I can hit 0.1 with our scale. You just force it in. That's the picture of 0.1, but like before, you zoom just right, you're going to be just fine. Let's see if we can fix that zoom. So if it's 0.1, then the horizontal extent should go from negative 0.3. That's 3 standard deviations to the left. That's 3 standard deviations to the right. And this looks like it should just be a little bit bigger. A lot bigger. Put a 1 in there. 2, 3, 4. There it is. That's the picture that we know and love. There's the normal model. So we can always, no matter how wild the parameters get back to that shape. Kind of cool in a way. That's why every time we do these problems, we always draw them in that same exact shape. But we're doing all this because it's good to know that when you're using this calculator, it's really working with something real. That curve has a formula. It's that formula right over here. But the larger takeaway is we're trying to get a better understanding of what the normal model is. So 1, 2, and 3 are kind of the bigger things about all of this. The fact that the total area is exactly 1, and doesn't matter how the shape looks, it's always a fact for every one of these displays. Total area of exactly 1, it'll never hit the x-axis. Well, that's a lot talking through these things. What we'll be doing in the next problems is the same as what we did before, except we're not using the 68 to 95, 99.7 rule. We'll include a graph just to organize the information, but all these problems going forward are going to be purely done with this calculator. These are just the picture in the back of our mind's eye of what we're really doing, finding areas under curves. Well, any last questions, folks, before we call it a night? It seems like a good stopping point. Awesome. When we come back on Wednesday, probably won't take too much time to work out these examples. So we'll be moving over into chapter 6, potentially end of Wednesday, or, more likely Thursday, I say. We'll be moving into chapter 6. We don't want to try to rush through this stuff. But have a great night, folks. If I did get your exam back, I have them down here. If you're participating virtually, don't hesitate to send me an email. I'm happy to scan it and just directly email it to you.
Thank you.
Yep, have a good one.
How are you doing, bud? Sorry, thank you. I'm not looking at you, but I was talking to you.
Yeah, how about you?
I'm good.
Good.
You surviving?
Yeah, are you?
No.
No?
No,
I've been on semester break even.
Yeah.
I mean, this one really not, but.
No, I had some.
Really?
And then I had to.
Me too, I got behind.
I'll be
this
very happy to
class,
help,
right?
Courtney.
No, yeah, no, I said.
I think I have like. two more.
Hey, my car.
Yeah.
Thanks, you too.
You okay with that?
Yeah.